So thank you all for coming, first of all. Are you having a good time on this conference so far? You do? Cool, perfect. I hope I'll continue that trend. So yeah, let me talk today about Celery on AWS, Elastic Container Service, the art of background task and continuous deployment. Before we jump straight into the mud of Celery and AWS, let me introduce myself. So my name is Jan. I'm coming from Slovenia. I'm staff software engineer at REN, where we are building a platform that helps people connect with their contacts. And by giving them a meaningful reasons to connect, we are tracking gazillions of news every day. And whenever there is something about your contacts, we let you know and draft a message using AI that helps you to reach out and to sell. So it's usually for C-level people in large organizations. I'm also author of tutorials and courses at test-driven.io on topics like Fast API, Flask, AWS, test-driven development, Python toolboxes, and so on. You can follow me on Twitter if you want, or add me on LinkedIn. You should have all the relevant information on the talks page on PyCon webpage. So let's start at the beginning. Async background tests. Why do we need them and what are they? So as soon as you go out of a simple tutorial-like application, or let's say a blog, you'll end up in a place where you need to solve some problems that might take a lot of time. So you'll need to run some tests that are running for a long time, and it's not appropriate to run that on your web server. So you need to put that into some background so that you don't have long outstanding requests, because having HTTP requests that takes 5 hours is not sustainable, right? Also, you might need to run some tests periodically. So you might want to schedule something for Monday morning, 7 p.m. or 7 a.m. and send some newsletter. You might want to implement things like retrying. So for example, when a user signs up to your application, you want to send welcome email, but you don't want to block them to not being able to use your application just because your third-party email service provider is down, right? So you want to throw that somewhere in the background and retry when appropriate, when it's back up, and then send them this welcome email, which welcomes them and tells them how much they need to appreciate your application and so on. So when you come to this set of problems, you need to find a way to run your task in the background. And if you're in a Python community and you're a Python developer, you'll probably go with Celery. There are other alternatives like Redis and so on, but Celery is pretty much the only one that is really battle tested and is running on large-scale projects, so you'll probably choose this one. In a nutshell, so Celery uses message broker like Redis or RabbitMQ. It also supports others like AWS ECS and so on, and workers. So when you want to run some task in your background, message is sent via message broker. Workers picks up these messages and process task appropriately according to your configuration in your code. It also comes with Celery Beat, which helps you to configure your scheduled task. You can use cron-like syntax, and you can define, I want to run something every 5 minutes, or 10 past every hour, or first of month at midnight, and stuff like that. When this decision is made, then the question is where to run your Celery workers. If you're already inside AWS ecosystem, I suggest to go with Elastic Container Service and Fargate underneath. Why is that? First of all, there is no provisioning of servers. Fargate is serverless service. You just need to define CPU and memory for your tasks to run, and some additional configuration, but that's pretty much it. Because there is no servers to patch, there are no servers to auto-scale and so on, it's fairly easy to scale your task up and down. So if you are using AWS console, you can just go there and just change one number and click confirm, and that's it. It's also fairly easy to set up auto-scaling. You can configure that based on memory consumption, CPU consumption. There are different metrics like average, max. You can use periods of 1 minute, 1 hour, whatever you want. And it's also fairly easy to deploy. So you can use AWS CLI or both of three, or any other way that's suitable for using AWS services. You configure some JSON, and there you go. That's it. So there are two parts of the configuration that are worth mentioning regarding Celery. So the first one is stop timeout. This is the time between seek term and seek kill when Elastic Container Service is killing your existing containers and starting new ones. We'll talk a bit more about that later when we'll talk about continuous deployment, but that's the stop timeout. So the largest value that you can use is 120 seconds. So use this one to give your containers as much time possible to gracefully exit. Also, the other one worth mentioning is minimum healthy %. So the rule of thumb is to go with 50%. This means that at all points in time, you will have at least 50% of desired targets running. So if you want to run 10 workers, at any point in time, regardless of deployments, scaling, and other activities, there will be at least 50%, so 5 workers running. You can experiment with that. You can use 100% if you want to be on top safe side. You can use 0 if you don't care if there is some downtime. But in general, 50% is a good value. So when you are running things on Elastic Container Service, especially in Fargate, you'll experience a lot of interruptions. And why so? When you will deploy, existing containers will be stopped and deregistered, and the new ones will start and will be registered. This means that every of existing container is killed. So seek term is sent. If after stop timeout container is still running for any reason, the Elastic Container Service sends seek kill and ungracefully kills everything. This also goes for scaling activities. So when you are doing upscaling, okay, there is no killing of containers, but when there is downscaling for any reason, whether it's auto-scaling or you manually scale your containers, you still have the killing of these containers. Elastic Container Service sends seek term. If container is still running after stop timeout, seek kill, and that's it. So what to do when you're in continuous deployment setup? So first of all, what does that mean? That means that you're deploying pretty much all the time. So the window between different deployments is very small, or at least should be very small. In the numbers, let's say 10 times per day. Depends on your team size, obviously. But as mentioned earlier, every deployment now is interruption. So our containers are getting killed, which means our Celery workers are getting killed. What we want to avoid for sure at this point is some long-running task like 5 hours, where we are not able to process such tasks during our office hours because we are deploying, I don't know, every hour, every 15 minutes, every 30 minutes. Because every time we come to a point where it's done some processing, there is new deployment, container is killed, and task needs to be restarted from the beginning. Also, there is a problem that task might be lost due to workers being ungracefully killed. As I said, seek term, 2 minutes, seek kill. If Celery is doing anything, when seek kill is sent, you might lose some tasks and they won't be processed at any point in time. So how to configure now our Celery workers to make sure that we don't experience these issues or that we control them and that we are not affected by these problems. So first thing is late task acknowledgement. By default, this is set to false, which means that tasks are acknowledged when workers receive them. In other words, worker picks up a message from the message broker, and at this point, task is acknowledged. If there is any exception during processing that task, or worker is ungracefully killed, or there is a nuclear explosion, or whatever, this task is considered as successful, and no one gives a shit about it. So first thing to do, late task acknowledgement, set this to true, so that tasks are acknowledged only after they are successfully processed. Okay? The next thing is visibility timeout. So by default, this is set to 1 hour. What is visibility timeout, which is set to 1 hour? This is time between task being received or picked up by a first worker. And if nothing happens with this task, so worker is killed or it's being still processed, another worker will pick up the same task after the visibility timeout. So it's set to 1 hour. If the task was interrupted during deployment or something like that, after 1 hour, another worker will pick up this task and try to process it. So what we need to make sure here is, we need to make sure that visibility timeout is always longer than the longest timeout for the task that we have. So we don't want tasks that might end processing for 2 hours in worst case, and visibility timeout at 1 hour, because this means that another worker will pick up this long task after 1 hour, despite it being processed on another worker, which will occupy our workers, and our throughput will obviously be lower than it could be. But on the other hand, we also want to keep that short, because if the worker is interrupted during deployment or downscaling activities, we want to make sure that another one picks up the same task as soon as possible. So we have these two mutually exclusive things. So we need to find some common ground or some value in between. And the rule of thumb, I'd say, is try for 15 minutes. Obviously, sometimes this is hard to achieve. So obviously use larger value. If you'll try to use smaller value, it will probably be too small. So try to aim to 15 minutes. Increase that if that's not suitable, but should be possible to aim that and also to achieve that. I'll discuss that a bit later, how to do that. So the next thing is countdown. Celery, in their documentation, is claiming that you can use countdown to execute your task at some later point in time. That is true to some degree, but there is a problem. So when the workers pick up tasks that have this countdown, they just store them inside their memory, and they're kept there until this countdown time passes. And that's it. So if you have a lot of such tasks, you may have thousands of messages inside worker memories. And if such worker is interrupted, guess what? These tasks are then again need to be picked up after visibility timeout by some other worker. And then you have this chain reaction where there are a lot of unprocessed messages for no good reason. So be very careful when to use it. Ideally, just don't use it. And also, be careful why. Because if the countdown is greater than visibility timeout, what might happen? Obviously, countdown, task, messages picked up. It's stored in memory of worker. It's there for 2 hours. Visibility timeout is 1 hour. Another worker will pick up the same message, and you'll have duplicated processing once again. So if worst case, if countdown is, I don't know, like 12 hours, you might end up in a state where every worker will process your task. So do you want to do that? Obviously not. The next thing is to reject task on worker loss. By default, this is obviously set to what? False. And why is that? Because there is a possibility that you end up in infinite loop of these messages in cases, for example, where your workers would be dying due to going out of memory. With Elastic Container Service and Fargate, this is pretty unlikely to happen. And even if it does happen, it's fairly easy to just increase the memory that's available to your tasks. It's super easy to do that. You can just change the number, redeploy, and that's it. So you don't need to worry much about it when you're running this in this setup. But yeah, be a bit careful. But in general, if you don't want to have lost tasks, do that. Because otherwise, if workers are ungracefully killed, this might just abandon some task in a queue, and it will never be processed again. And yeah, that's a problem even with the late acknowledgement, as stated on slide. So late acknowledgement is not enough. The next thing is prefetch multiplier. So by default, this is set to 4. The reason for that is to reduce overhead when fetching new messages from the queue, so that whenever one task is processed, another one can be picked up immediately. But if you don't have super short tasks, this overhead is too small to really make sense to care about it. But one thing that might happen here is that you will have 4 tasks that will be retried only after visibility timeout, because obviously the worker that is killed during deployment already picked up 4 messages instead of 1. So don't use default 4, update this to value 1. And last but not least, Celery configuration is signal remapping. All the others that I mentioned so far, you can find this inside Celery documentation, and yeah, you might struggle to go through everything, but it's not too bad. But this one is the hardest one to find because there is no mention of it inside Celery documentation. The only place that mentions it is some guide for Heroku, how to run Celery workers there, because it's not even Celery's feature, but it's Billiard's feature, which is a library that Celery depends on to manage multi-threading and multi-processing. So by default, if Celery receives seek term, it gets to worm shutdown. This means that it tries to process the current task and exit after that. But as we are limited with these 2 minutes of stop timeout in Elastic Container Service, what might happen is that the task is still not finished, but it will be ungracefully killed by the seek kill afterward, after 2 minutes. So what we can do is to remap seek term to seek quit signal, and then Celery goes to cold shutdown, which essentially ends up in the same state as if the worker is lost for out of memory or anything. So this goes then to this reject task on worker loss. So if we don't want to lose our task for good, we need to remap these signals, and we can do that by, setting remap seek term environment variable to value seek quit. Okay, so the example configuration then looks like this. So this is your Celery app, visibility timeout, late acknowledgement, reject on worker loss, and prefetch multiplier. And when you start your worker, you just need to set up the environment variable for signal remapping. Okay, so we have now this Celery configuration, and that's great. But we still need to manage our tasks and to use them in a way that support all this configuration and this continuous deployment setup. So I was talking about 15 minutes of visibility timeout and how to get there. So there are some attributes or properties of our task that we want to achieve in order to successfully process as much as possible and as reliably as possible. So first thing is we want to make sure that our tasks are short. Try to aim to max execution time or processing time of 15 minutes. Sometimes not possible, but there are techniques to get there. Obviously, if we are talking only about the application tasks, not some long ETL pipelines, which are not part of the application itself. And try to keep the typical processing time under 2 minutes, also possible. We need to make sure that our tasks are idempotent. So this means that every time we run them, they need to produce the same result. And if we run them multiple times, things must still work. Nothing must explode. And also, we must be able to have retries one way or the other. But the best way is to have exponential back-off retries with jitter, so that if there are some issues, for example, with third-party APIs by hitting rate limits or stuff like that, that we don't just retry with hundreds of tasks all at the same time and then maybe process 2 or 3 tasks successfully, but everything else is hitting rate limits. With jitter and exponential backoff, we spread this a bit more randomly over time and make sure that things can go through a bit more smoothly. So the idempotency can be pretty domain specific, so we won't talk much about it today anymore. Retries with Celery are fairly simple to configure. You can just refer to official documentation. There are a couple of parameters that you need to change, and that's it. So we'll mostly focus on how to keep these tasks short. So let's start. What we want to achieve is to have maximal processing time of our tasks shorter than the window between deployments. That's our goal. So the first thing that we can do is to do fan out. So if we have send emails to users, one job, which takes n users and seconds to process, we can split this into two layers, where in the first job, we list all the users. In the second set of jobs, we actually send emails. This way, we make sure that the second jobs, so the ones that are sending emails, are roughly processing in constant time. And the first one is growing with processing time much, much, much slower than the first one. There are also trade-offs, as with any other thing. So we should use that only when we have a high priority task. So if everything else that will come after these tasks were submitted, we'll need to wait for all these tasks to be processed, because all the workers will be occupied with all these tasks that were submitted from this fan out. So if these are not high priority tasks, then don't use fan out, but use something else, because everything will be jammed. You can also use that in multiple layers, obviously. So for example, for every user, every post, every comment, there can be a job. So you can really go a long way with that. Another option is to use batching, which looks like that. So instead of having this single job here, which is the same as the previous one, we split the processing into smaller batches. So for example, we process 100 users at a time. If there are more users to process, we resubmit same job, just with some cursor which tells where the last job finished, so where we need to continue. I'll quickly show the example later. So this way we make sure batch processing time is then roughly constant, so 100 users is 100 users. If we need to process million users, we just need to have more jobs to do that. If there are no users to process, we exit from the last job, and that's it. This way, we occupy only one worker at a time, but it takes more time to finish the processing, and also it's harder to implement compared to fan out. The last thing I wanted to mention is task locking. So we don't want the workers to pick up, two workers to pick up the same task. So we can use locking with Redis to make sure that we avoid that. If we cannot acquire a lock, we can ignore task. This is also described in Celery official documentation. We can just drop it, but with this, we might have lost task again. We can resubmit same task with new ID, but same arguments. This way, we make sure that at least once we process every unit of work that we need to process, or we can retry. The last one is conceptually the most correct, but if you have little number of retries set, so for example, 2 or 3, you might end up in running out of retries if there are a lot of interruptions, for example, deployments one after the other. So yeah. That's it regarding the theory. We ran out more or less out of time, but you can find a working example on GitHub repository, Celery ECS examples on my profile. And there are code examples, and there are also the resources which I use to prepare this talk. I think we don't have much time for questions.
Yes,
we do? OK, then I can answer some questions, but if there are more questions, you can ask me after the talk. We can discuss it outside.
So, a quick roll-up. Do you have some useful tips to catch some of these undesired behaviors caused by Celery misconfiguration in test environments? So,
not really. I mean, what we use at RAN is a dashboard on Grafana, which is tracking all the events that are submitted from Celery workers, because there are a lot of different events submitted, like task sent, task received, task started, task retried, task failed, and so on. And then we have dashboards drawn there on production, obviously, where we are alerted if there are any strange things going on, for example.
Next question. What are the benefits of using Celery with ECS ECS instead of Lambda?
What are the benefits? I mean, the main benefit is that with Celery, you can set up the whole environment for your application locally. If you are using Lambda with, for example, SNS or SQS, you have this need to run everything on cloud, and locally it's very hard to reproduce the exactly same setup. And yeah, there are also other limitations from Lambda. For example, there is hard limit on 15 minutes timeout. There is lower limit for RAM, I think also for CPU resources and so on. But in general, you can use whichever solves your problem. So I'm not a huge advocate for Celery. That's just what we are using at this point. But who knows? Maybe not for forever.
So one last question. Why two Celery workers might get the same task?
Why? That's a good question. The simple answer is because they can read the same message. The locking that's done for preventing reading the same messages is not very clever. Also, there are a lot of other implementation details when you dig into the Celery's code and the Celery protocol, which are a bit fishy. So yeah, I mean, this is classic race condition problem. So there is one message which can be read by two clients, and then there you have duplicated processing.
So we have another one. How can I ensure that the right worker is stopped when the auto-scaling policy scales down the number or Fargate task? Very specific question. Maybe.
You can't do anything about it. When downscaling is done, if you downscale, I don't know, from 10 to 8, 2 workers out of 10 are killed randomly. There is no pattern. Elastic Container Service doesn't know anything regarding what is being processed where. So it might be a worker that does nothing at this point, or it can be a worker that's processing the task for the last 2 hours and it's still not finished. So not much you can do here.
So